Good afternoon, folks. How are you today? We are going to continue talking about solving a linear system. So we have a square matrix A times X is B, and we know that this B is not zero. So we know A, we know B, we want to find X. So there are two categories of methods, one called exact methods. So these are mathematical methods. If we do them with perfect machines, we will get true solution or exact solution. So there are essentially within exact methods, there are families of methods called elimination methods, among them Gauss or Gauss-Jordan elimination. There are LU decomposition methods, and there is the concept of matrix inversion. So we are going to talk about Gauss-Jordan elimination and matrix inversion. Now, those of you who have taken a linear algebra course, we are going to do our elimination differently because our focus here is to minimize round-off errors in computing machines. Whereas in linear algebra course, you always assume that your arithmetic is perfect, no round-off errors. Then we are going to take a look at second category of methods called iterative methods. And again, there are quite a few of them. We are going to focus on Gauss-Seidel method, which is the most common one. So let's start talking about Gauss-Jordan elimination method. Gauss-Jordan elimination method has two stages. First stage is we transform our system AX is equal to B into a system dx is equal to b prime. So this D matrix is a diagonal matrix. And then in the second step, what we do is, since now this is a diagonal matrix, any x would be the corresponding B element divided by the diagonal element corresponding. And this would be true for all of our unknowns. So let's visualize this. What we want to do is we want to transform a matrix A. Since we don't know X at all, let's not even bring X into the picture in stage one. And this is B. So what we want to do is we want to transform this into a diagonal matrix form. That means we want zeros elsewhere. So what we do is to get into the shape, we get zeros. First we get zeros in first column, then we get zeros in second column, then in third column, and so on and so forth. So when we are doing this, when we want to get zeros in first column, we call it first step. Then we have second step. So for steps k 1 through n, we want to get zeros in first column. So we will modify all rows except the first row. So first row becomes our what is called pivoting row. And this first column becomes our pivoting column. And this first column, first row, first column element is called pivoting element. So what we are going to do is we are going to modify all rows except the kth row. And how are we going to modify it? We are going to take the ith row and subtract from it a multiplier times the kth row. Remember, kth row is our pivoting row. So this multiplier is a ratio of element aik over akk. So this you recognize, this is our pivoting element. And this is the element that we want to get 0 in. So you will see in the examples. But anyway, this elimination method requires n cube over 3 multiplications. And this you saw was vastly superior to Kramer's rule. So I don't know if you remember. Let me take out one of my old notes. So in my old notes, you will see I had written that for, if you use Kramer's rule, if the size was like 100, we would have never solved it. But now we use elimination methods. Even on a very old computer, it takes 25 seconds. And on a modern computer, it'll take only 25 microseconds. So let's do an example. So let's consider we have a 3 by 3 system, which is 1x1 plus 2x2 plus 1x3 is equal to 0. 2x1 plus 2x2 plus 3x3 is equal to 3. And then minus 1x1 minus 3x2, no x3, so we'll write as 0x3 is 2. So our size of the system is 3. And let's write it in a matrix form. So we'll pick up 1, 2, 1. And since we don't know x's, we won't write them, so we'll just write b as 0. 2, 2, 3, 3. Minus 1, minus 3, 0, and 2. So this is our matrix A, 3 by 3. This is our matrix B, 3 by 1. And we call this an augmented matrix. We augment A by B. So our goal in the first step is to get zeros here. And this is our pivoting element. So what we'll do in first step is, since this row is our pivoting row, we are going to take this second row, subtract from it a multiplier. So our multiplier is, we want to get a 0 here. So 2 divided by 1 times our first row. For third row, our multiplier is going to be minus 1 over 1 times the first row. So you'll see this written with colorful notation here. So our first row remains unchanged, 1, 2, 1, 0. So this says that we are going to subtract 2 times the first row from second row. So 2 minus 2 times 1, 2 minus 2 times 2, 3 minus 2 times 1, 3 minus 2 times 0. That's what we will get. This says we are going to add third and first row. So we are going to add third and first row. 0 plus 2 is 2. So we have finished first step. We got zeros here. Now in second step, we want to get a 0 here, a 0 here. This is our pivoting element. So this is our pivoting row. So we are going to take first row, subtract from it a multiplier. Remember, denominator is pivoting element. Numerator is what we want to get 0 times pivoting row was second row. So now we are going to take third row minus 1 over minus 2 times second row. Okay. So this is what I wrote in a colorful way. So let's see our result. So second row remains unchanged. First row and second row we add. That's what this means. This says we subtract half of second row from third row. Okay, so we have finished step 2. Now we are in step 3. So in step 3, this becomes the pivoting row. So this is our pivoting element. We want to get zeros here. So when we take our first row, from here we are going to subtract 2 over half times our pivoting row. From second, we are going to subtract 1 over half times the third row. So this is what is here. So our third row remains unchanged. From first row, we are going to subtract 4 times the third row. 4 times the third row. 4 times the third row. Here we are going to subtract 2 times the third row from second row. 3 minus 2 times half. So you can see we got a diagonal matrix is B prime. So now we normalize. So we say x1 is 1 over 1. So we'll get 1. x2 is 2 over negative 2. So we'll get negative 1. x3 is 0.5 over 0.5. So we will get positive. So our answers are 1, -1, +1. So we verify, put it back in our original equation and see that our right hand side matches. Okay, so that is Gauss-Jordan. Then we have matrix inversion. So we know that we have a unique solution only if determinant of A is not 0. So if determinant of A is not 0, then A inverse exists. What is A inverse? If we take A multiplied by A inverse, or if we take A inverse multiplied by A, we'll get the same result. So A inverse is like 1 over A, if you think like that. But of course, we don't have concept of division, so we don't show that algebraically. But anyway, what is the advantage of having A inverse? Suppose we have a system AX is equal to B. We pre-multiply both sides by A inverse. And you can see this is I. And of course, I times X is just X. So if we had A inverse, we can just get X by multiplying A inverse by B. But the question is, how do we find A inverse? Well, we use Gauss-Jordan method to find A inverse. So we see we have A times A inverse is equal to I. We know A, we know I, we want to find A inverse. So we use Gauss-Jordan method. And what we do this time is we augment A with I. So let's go to our matrix. So this is the same matrix A that we have. I have augmented with I, and we want to find A inverse. So here we go. Our A matrix was 1, 2, 1, 2, 2, 3, -1, -3, 0. We augmented with I matrix. So this is A, this is I. So this is our pivoting row. We'll take second row, subtract. We want to get 0 here. So we will have 2 over 1 times first row. Third row, -1 over 1. So we are basically repeating the same step as we just did. So first row doesn't change. Second row, we are going to subtract twice the first row. From third and first, we are going to add them. So we got our zeros here. Now this becomes our pivoting row. This is our pivoting element. So we'll take first row, subtract from it 2 over -2 times second row. From third row, -1 over -2 times second row. So basically we are adding first and second row. So we'll get We didn't change second row at all. And we are subtracting half of second row. Sorry, 1 minus half of 0. Okay. So now this becomes the pivoting row. This is our pivoting element. So we are going to take first row minus 2 over half times third row. We are going to take second row 1 over half times third row. So we are subtracting 4 times the third row from first row. So we are going to get 1, 0, 0, minus 1, minus 4 times 2, minus 9, 1 minus 4 times 1, and then we will have 0 minus 4 times 1. Second row, we are going to subtract twice the third row. So we get 0, twice the third row, minus 2, twice the third row, 0, twice the third row, minus 6, twice the third row, and twice the third row. Third row remains unchanged. So you can see we got a diagonal matrix here. So we are going to normalize this side. We are going to divide this by 1, divide this by negative 2, divide this by 0.5, and this is where we are going to get A inverse. So we'll say A inverse is, so we normalize, minus 9, 3, minus 4, divide this by minus 2, so we will get 3, negative 1, 1, divide this by 0.5, we'll get 4, negative 1, 2, and that's our A inverse. So then we multiply this by B, and we will get our X. Now, just for those of you who have not done enough matrix manipulations by hand, please manually do this by hand. Try A times A inverse. So you have A, you know A inverse, multiply it, make sure you get I. Take A inverse, multiply it by A, make sure you get I.